direction of deep learning in this seminar. Today, I'm going to talk about two-layer neural networks for solving PDEs. I will actually talk about observation, optimization, and generalization, but I will focus mainly on the optimization and generalization, and will only briefly introduce the approximation to motivate why we want to use neural network to solve PDEs, especially high-dimensional PDEs. So the take-home message is that if we use neural network to solve high-dimensional problem, we can prove that neural network it's a very powerful tool to approximate high-dimensional functions, probably without the curse of dimensionality, which is the main benefit we hope to use to solve high-dimensional PDE. We usually need to use optimization method to identify the set of parameters in a neural network so that this neural network can approximate the solution of the high-dimensional PDE. So we also wonder whether we can prove that numerical optimization is efficient, especially aiming at proving that we can get a global minimizer of the optimization algorithm. Once we have the global minimizer of the optimization objective function, we wonder how good the solution is. Usually, we just sample a finitely many sample to define a loss function, and we minimize the loss function to get a solution. But the solution need to generalize well to unseen data. So we also wonder how good this generalization error is if we use neural network to solve high-dimensional PDE. So to the best of my knowledge, we can prove some optimization global convergence to the global minimizer with very strong assumption. And it is very difficult to weaken the strong assumption. The assumption is quite strong in the sense that it is challenging or almost impossible to verify the result numerically, as we will see later. And we can also prove that the solution can generalize well. We have good scaling in terms of the generalization error. It decays fast, probably without the curse of dimensionality, when we increase the number of samples. However, there is some gap between optimization and generalization. In typical generalization analysis, we have to put some regularization to restrict the search space of the network parameter so that we can get good generalization. However, when we prove optimization convergence, we don't have any constraint. With constraint, we don't know how to prove the convergence to global minimizer. Without the constraint, we don't know how to prove small generalization error. So there is some gap between the optimization and generalization. So in sum, the story I'm going to share, there are some individual stories having their own merits, but it's still challenging to get a complete story to fully understand the theory for deep learning to solve PDEs. There are many open problems interesting to explore, and if you're interested in this direction, please feel free to ask questions and discuss after the talk. So what is neural network? From my point of view, neural network is just the composition of some simple functions to generate a very complicated function. For example, we might have L simple function Hi defined using the linear transformation in X with parameters W and B, after which we have a nonlinear activation function acting on this resulting vector entry-wise to get the output of the Hi function. If we compose this LHI function together, and finally we we also apply a linear transformation denoted by t. Then we can get the final output y of the neural network H. So this is a neural network. We generate a complicated function using the composition of simple functions. So we are going to use this special parameterization method to parametrize the PDE solution and apply it to solve PDE. That is the deep learning based method for solving PDEs. We're going to use this neural network in the sense of supervised learning to solve PDE. What is supervised learning? In supervised learning, we usually have some unknown target function f to be recovered. But we don't know the f explicitly. We only have some sample location xi and corresponding the function value yi of f. We want to construct a family of neural networks H and identify the best one among this family of neural networks so that the best neural network can approximate the unknown function f quite well. How can we identify this best neural network? We will formulate an optimization problem to identify the best neural network approximating the unknown function f. In the ideal case, if we know the function f, then the so-called population loss function Rd is the ideal criteria to quantify how well f approximating the function f, because it considers all the possible sample locations. However, usually we don't know f, and we don't know how we sample the location x. So it is not practical to compute the population loss. It's impossible to compute that. We only have finite samples, xi and yi, so we can define the empirical loss function denoted as Rs as the approximation to the population loss function Rd. You can see that actually this is the average of n samples of the random function. If you think about this function in x as a random function with a random variable x, then the empirical loss function is the average of n samples approximating the population loss function. So once we have the Rs, we can compute that. We can also compute the gradient of Rs with respect to the parameters. So a very natural way is to design some optimization algorithm, for example, gradient descent or stochastic gradient descent, to minimize Rs to obtain a solution, numerical solution, denoted by theta n. Usually, due to some numerical error, due to noise, due to the fact that maybe you cannot identify the global minimizer of the objective function, the numerical solution theta n might not equal to the global minimizer theta s of the empirical loss function. And of course, the global loss of the empirical loss function might not equal to the global minimizer theta d of the population loss function. So theta d is the best solution we want to get, but in fact, after numerical computation, we can only get theta n. So you might wonder how good theta n is compared to theta d. So we can simply substitute theta n into the population loss. If the population loss evaluated at theta n is very small compared to the population loss evaluated at theta d, then we can believe that theta n is a good solution. In the theoretical analysis, how can we analyze how large Rd theta n is? We can use some triangular inequality to get individual terms to analyze. For example, you can check the first identity because all the other terms, they're cancelled to each other. So if we agree with this identity, next, we go to the third term, because theta s is the global minimizer of the empirical loss Rs. So this means that Rs theta s is less than or equal to Rs theta d. So if we ignore the third term, then we can have the inequality. We just simply copy down the other terms, adding some colors to distinguish these terms. We have the blue term, the red term, and the black terms. We can apply different techniques to analyze this term individually. If we can apply some theorem to show that all these terms are small, that means that RD theta d is small, and we have a full error analysis of deep learning. Now let us look at the terms individually. In the blue term, by definition, it's the population loss at the global minimizer theta d. So of course, it's less than or equal to the population loss for an arbitrary parameter set theta tilde. So if we are able to construct a set of parameter theta tilde such that the neural network can approximate the target function f well in the L2 norm sense, then we can use this approximation error to bound the blue term. So this is the approximation theory of deep learning. Next, if we are able to prove a certain optimization algorithm can give us a global minimizer, then theta n will be equal to theta s and the red term will be equal to 0. If we cannot get global minimizer, we wonder how good the global minimizer we can get through the optimization algorithm. So the red term is called the optimization error. And finally, the black terms, they are related to the generalization analysis because it quantifies how well the neural network can generalize from the finite sample in the empirical loss function to the population distribution in the population loss function. So today I'm going to talk about some theory to understand all these terms individually, but still we don't have the complete theory to prove that RD theta n is small. So I have introduced the supervised learning setting and the methodology to analyze the error of supervised learning where we use neural network to solve supervised learning problem. Next, I'm going to talk about solving PDEs, how we can use supervised learning to solve PDE based on neural networks, especially for especially when the problem is high dimensional. In the traditional solvers, it is not affordable to solve it high dimensional PDEs. So this motivates people to explore using neural network to solve high dimensional PDE. I spent some time in the literature, and I realized that actually 30 years ago, people have been trying to use neural network to solve PDEs. For example, they in these papers, they apply usually shallow neural network, probably order 1 layer neural network in the least square sense to solve PDE. What is the least square sense? I will give you an example later. And more recently, because deep learning has been very popular, people have been trying to use deeper and deeper neural network and all kinds of neural network designed in the computer science to solve PDEs. Some people also use the least square sense. For example, the work in the DGM and the work in PIN. And some other people might design some other loss function based on variation principle, for example, deep risk method to solve PDE. For simplicity, let us look at the least square sense, how we can use the least square sense combined with neural network to solve PDE. So let us look at a boundary value problem where D is a differential operator, B is a boundary operator. We have a boundary value problem. We can reformulate the PDE problem using the least square idea. For example, we try to minimize the loss function. If we use a neural network to parametrize the solution of the PDE, then the problem becomes the problem to identify the set of parameters such that the neural network can satisfy the differential equation together with the boundary condition in the sense of least square minimization. So in my point of view, this is essentially a special kind of supervised learning, because if you just look at this term, if the boundary condition is the derivative boundary condition, then we can forget about this B. We just want to find a neural network fitting a given function on the boundary. So this is a supervised learning problem. And as for this term, you can think about D acting on the neural network. It's a new neural network. And we use this new neural network to fit the right-hand side function f. So this is, again, another supervised learning problem. So that is why I claim that we can use supervised learning to solve PDE based on neural network. In numerical computation, we usually randomly sample the sample to evaluate the loss function, because the original loss function it's not possible to evaluate that because of the continuum L2 norm here. We usually random sample to evaluate the discrete version of it and try to minimize that. So this is the basic idea about using neural network to solve PDEs. So why we want to use neural network to solve PDE, and how we can justify this solver. People believe that neural network is very powerful to approximate high-dimensional function so that we can solve high-dimensional PDE. So in theory, the first question we need to discuss is that, is it really true that neural network can approximate high-dimensional function to justify the application of neural network to high-dimensional PDEs? I would say this problem is relatively clear because there has been many papers discussing the approximation power of neural networks. In the interest of time, I will just list some results to help you to understand the status. For example, we look at the d-dimensional continuum function. We try to understand how good Relu neural network can approximate d-dimensional continuum function. Usually when we design PDE solvers and use a neural network, the first question we want to answer in the numerical solver is how large the neural network should be. For example, what is the size of the width, what is the size of the depth. So it is very important to understand the approximation power of a neural network with a given width n, a given depth L, so that we can choose the appropriate n and L for our target accuracy. So we have characterized a nearly tight approximation rate in terms of the width n and depth L to approximate d-dimensional continuum function. But unfortunately, according to our nearly tight approximation rate, in other words, this is the approximation error, the best approximation error we could expect in terms of the width n and depth L. We have the curse of dimensionality because of the term 1 over d here. Here, omega f is the modular continuity. In a very simple case, when the function f is a Lipschitz continuum function, you can think about omega f as a linear function with slope equal to the Lipschitz continuum constant. So you can kind of ignore that. part and just focus on the rate in terms of N and L. So we can based on this error, we can prove that fix the target accuracy epsilon, then the number of parameters required to achieve this epsilon accuracy might scale exponentially large indeed. So this is the curse of dimensionality. So the result means that this is bad news. If we use the rule neural network to approximate high dimensional function, then we have the curse of dimensionality. People also try to explore whether smoothness in the function can help. I would say that it could help a little bit, but if the smoothness is finite and when D is very large, if we allow D to change, go to infinity, then we have a nearly tight approximation rate for CS function with the rate here. If S is fixed and D is changing, then because of the 1 over D factor here, we still have the curse of dimensionality. And the approximation error will be bad if we require higher regularity in the norm to measure the approximation error. For example, if we use the Supervised norm to characterize the approximation error instead of the L infinity norm, then we can see that we have a worse approximation rate. So these are all bad news for rule neural network to approximate high dimensional function. So what is the good news? The good news is that if rule neural network is not working for high dimensional problem, why not just change some other activation function? And luckily, we can prove that if we use some other activation function like the floor and rule activation function, then we can get much better approximation rate in terms of the width and depth. For example, if we look at the width here, sorry, the rate here, then we don't have the 1 over D factor anymore, which means that we don't have curse of dimensionality. We have a very small factor depending on the dimension D. It's the square root of D, so it is not a matter. And according to this result, if we increase the depth, the error can decrease root exponentially fast. So this is some evidence to show that it is good to use deep neural network. And deeper is better. Increasing the width is not as good as increasing the depth. So this is one story, but we're still very curious about whether it is really true that width is not as powerful as depth. Because this is an interesting question in deep learning theory. People have many results showing that deeper is better. So we just wonder whether wide neural network is as good as deep neural network. So recently we have an answer to this question. So we just use one more special activation function, like the exponential activation function. Then we can prove that a neural network with depth 3 is enough to be powerful. For example, we just increase the width and we can get a very good approximation rate in terms of the width n. It's exponentially fast decaying when we increase the width n faster than the rate in terms of depth in the previous result. So this means that if we choose the activation function appropriately, shallow neural network can also be very powerful. So this is a very interesting result, but if we look at this result, we still have to change the size of the neural network according to our requirement of the accuracy in the PDE solver. So we just wonder whether we have some theory showing that a fixed size of neural network can achieve arbitrary small accuracy. If this is true, that means that it is not it is we don't need to consider the problem to decide how to decide the width and the depth. We can have a universal size of the neural network for our application. We don't need to care about the accuracy in terms of the width and depth. So more recently, we discovered that there exists some simple activation function. For example, the example here, on the negative side of the domain, we have the soft plus function, which is a common activation function in CS. On the positive part of the domain, we have the sawtooth function. And this activation function is a continuous function. And we can prove that if we use the activation function to construct neural network, a small neural network is powerful enough to approximate high-dimensional function. For example, the width can be a fixed number, order d squared, and the depth can be a fixed number, 11. No matter how large no matter how small the accuracy that is, we can still identify a neural network by only changing the weights of a fixed size architecture to approximate an arbitrary d-dimensional continuous function. So this story means that neural network approximation indeed is very powerful to approximate high-dimensional function. And this is the almost the end of the approximation theory of neural network. In fact, we can also, based on the continuous activation function here, we can also construct CS activation function and sigmoidal activation function with the same super approximation power, in the sense that a fixed size of neural network can approximate high-dimensional continuous function within arbitrary small error.
So Haizhao,
yes.
Can I ask a quick question? So what is the sigma
Sure.
beyond the 10? So it's like periodically. So you only show the picture of sigma. Can you go back to the page? Yeah. You only show the picture of the sigma between negative 10 and 10. What happened to the value greater than 10? It's just the
outside.
The same.
Yeah.
Okay.
So I defined the activation function. When x is less than 0, it is a soft plus activation function.
Okay.
So it is a function with a configuration like this and approaching to -1, all the way going to the negative infinity. And on the positive side, it's simply the sawtooth function. You just repeat this pattern.
So you sort of encode this one, like Yarovsky, when he proved he has this kind of function when he proved the product or whatever, and here you encode this in the activation function.
This sawtooth function is the most fundamental breakthrough when people try to understand the approximation power of neural network, ReLU neural network. In the paper by Yarovsky, he discovered that we can use ReLU neural network to approximate sawtooth function with exponentially fast convergence rate. And the sawtooth function can be used to approximate polynomials with exponentially fast approximation rate. So this is the first breakthrough trying to understand the power of the ReLU activation function. But in his paper, because he used ReLU activation function, which means that power is limited. You don't have enough teeth here. So if we directly use sawtooth activation function, you have enough teeth here. You have infinitely many teeth here, so that you can construct very powerful neural network.
Yeah, I understand. Yeah, I sort of get that part. But how do you change the resolution of the teeth? Because the depth is like given, and width is also fixed. You may need to change the resolution of the teeth. Which part you can see that?
It's the power of the function composition of periodic function to guarantee that a fixed depth is enough.
But you only like compose like 11 times, right? So I assume.
Yeah, we compose 11 times. So even though we just compose 11 times, but we can adjust the parameters.
Okay.
By adjusting the parameter, you can have some rescaling of the activation function. For example, if you put some rescaling parameter inside the activation function, you can squeeze the activation function so that you have it has sufficient many t for you to use.
Okay. So you encode.
So we just discovered
that type of function, like mother function, as activation function to generate the larger class of the hypothesis. Functions. Okay.
You're right.
That makes sense.
So the basic idea is to treat neural network as a powerful encoder and decoder.
That makes sense. I have some other question I'll ask you after talk. Yeah, go ahead. So sorry.
Thank you. So this is the first part, but the bad news is that still we don't have numerical algorithm to implement that because we require exponentially many samples in the construction of our neural network, and the precision in the neural network, the parameter has high precision in the neural network. As I mentioned, it's essentially an encoder. If we have exponentially many samples, we just use small neural network to encode those samples in a small neural network, and there's no free lunch. So the number of precision might be exponentially large in the small neural network. But if you have a nice function, maybe you can prove that the precision is not large, and you can avoid the curse of dimensionality also in the precision. So this is the first part. So next, how can we use neural network to use optimization to identify the parameters in the neural network, and how good the generalization error is? So I would like to talk about the Ntk theory for optimization. It is one of the two methods for optimization analysis for global optimization, global minimizer of the optimization. It was first proposed in a paper 3 years ago by Jacob, where he studied two-layer neural networks, and some other researchers have been trying to generalize this result using similar ideas to multi-layer, to different kinds of activation function, and also try to get some generalization theory. So to the best of my knowledge, there might be probably these two papers addressing the optimization and generalization with consistent result without a gap I mentioned. Recall that I mentioned that there is a gap between optimization and generalization. The condition for both, there is no consistent condition for both theories work. Probably these two papers are the only two papers talking about consistent theory. Or maybe I'm wrong, maybe more recent there are more paper coming out. So I want to recall that comment. However, the condition in these papers are not very straightforward to be verified in real applications. So it is still some way to go to get consistent result with good assumption that can be verified or can be easily understood. In the direction of solving PDE, the optimization analysis was opened. So how can we apply the Ntk theory to understand the optimization convergence for deep learning? Let us use the optimization analysis for regression problem based on two-layer neural, just for regression problem for simplicity to understand the key idea of Ntk. Later, I will apply two-layer neural network to try to develop some theory for the optimization in deep learning-based PDE solver. So what is the main idea of Ntk? Let us recall the objective function in empirical loss function. We want to minimize this empirical loss function. If we use gradient descent, for example, to update the parameters, then we have the gradient descent updating rule coming from the gradient of the loss function with respect to the parameters. If we introduce some notations here, then we can get some simple formula to represent the dynamic of the gradient descent. Next, if we take the step size tau go to 0, then we can get the gradient float to work on, because it's easier to work on the gradient float instead of the PDE computation in the gradient descent algorithm. So this is a nonlinear ODE for the parameters. If we are able to solve this nonlinear ODE, then we can get explicit formula for theta t to help us understand the evolution of the parameters of the neural network, to help us to understand the evolution of the neural network, whether in the end the neural network can converge to a function that can predict all the training sample very well, or in other words, whether the neural network can converge to a function that can minimize the empirical loss function very well. So the key is to get the solution of this nonlinear ODE. But because of the nonlinearity, it is almost impossible to solve this nonlinear ODE. So this is the main difficulty. Similarly, based on the nonlinear ODE for this parameter, we can obtain the nonlinear ODE for the evolution of the neural network. For example, we just compute the derivative with respect to the iteration time t of the neural network. By the chain rule, we can get the second term. By substituting the ODE for theta t, we can get the last term, where we have introduced the notation called Ntk, neural tangent kernel. So the neural tangent kernel is a key quantity to help us to analyze the convergence and also the appropriate generalization of two-layer neural network for solving PDEs. So unfortunately, the evolution in theta, the evolution in the neural network H, they are both nonlinear ODEs. It's impossible to solve that. A very natural idea is to linearize that to get simple objective to analyze. For example, if we take first order observation using the Taylor expansion at the point theta 0, then we can obtain the first order observation here, denoted as H length, to approximate the original neural network. If we compute the derivative with respect to t for this H length function, we can obtain the dynamic for the H length function using similar argument. And if we look at the dynamic of this for this H length function, we see that it's a linear ODE. Once it's a linear ODE, we can solve it to get explicit solution. For example, if you believe me, we can get the solution here for the H length function. And if we substitute the training sample into this function and do some calculation to simplify the notation, we can get the fact that the H length evaluated at the training sample is equal to the right-hand side function here. So now you can see why I claim that the Ntk, the capital K matrix, is very important to understand the convergence. Because if the Ntk is strictly positive definite, then the second part will approach to 0 when t go to infinity. And the first part here will approach to an identity matrix when t going to infinity. So the right-hand side will go to the correct label y that we want to classify it, which means that when t go to infinity, then the H-length neural network will approach to a function that can exactly classify all the training samples. In other words, we get the global minimizer of the empirical loss function. But you might argue that this is only the result for H length. How about the original neural network H? Yeah, this is a good argument. So if the first order approximation here is very accurate during the whole training time t, then each lane can approximate the neural network H quite well. So if each lane can classify all the samples correctly, then we can understand that H can also classify all the training samples correctly, which means that we have the chance to prove that the gradient descent can help us to identify a global minimizer of the empirical loss function up to some approximation error highlighted here. So this is the main idea of Ntk. So how can we go through the proof to get rigorous result? The key is to understand the approximation in the Taylor expansion throughout the training time. So let us, for simplicity, let us look at two-layer neural network and begin with classification. Begin with regression instead of solving PDE using the rule activation function with some special initialization where we have a gamma, a small number to control the outer linear transformation parameter. This control is very important as we shall see in the proof. The intuitive understanding is that we want to control the outer linear transformation to be very small so that even if after convergence, the outer linear transformation won't change too much. And actually, we can also prove that under some condition, the W parameters will not change too much, but we can still fit all the samples. So how can we measure that? I will tell you how to get it rigorously. And again, if we introduce notation, if we substitute, we want to introduce some notation to get some neat formula to understand the theory. So we can introduce the prediction error denoted by E. It is the prediction error at this ith sample x by the neural network H. So we can simplify the empirical loss function using this notation E. And according to the gradient descent dynamic, we can get some inequality later to bound to understand the evolution of the loss, and we can prove that the loss can gradually decrease to 0 when the training time t go to infinity under certain condition. So in the intuitive illustration of the main idea of Ntk, we have defined the Ntk kernel matrix. Actually, we would like to decompose that kernel matrix into two parts. In the original definition of the Ntk matrix, it is the multiplication of the derivative of the neural network with respect to all parameters. I'm going to decompose this Ntk matrix into two parts. One part for the outer linear transformation for the parameter A, and the other part for the parameter W as the first linear transformation parameters in the neural network. So that is why we introduce the kernel, the discrete Ntk kernel, the Ntk kernel with respect to the A in the outer linear transformation based on the formula here, and the kernel with respect to W in the first linear transformation with the formula here. So we can understand that we are going to solve the convergence analysis mainly based on the behavior of the Ntk with respect to A. So if we assume that at the initialization, the Ntk based on A has a positive smallest eigenvalue, then under certain condition, we can prove that gradient descent can identify the global minimizer of the empirical loss function in the regression problem. So how can we go through the steps to prove that? The idea is that according to the gradient descent formulation, we can get the dynamics for the neural network and also for the empirical loss function. We can verify that by simple calculation, the derivative of the loss function is equal to the notation here, where E is the prediction error we introduced in the previous slide. So from this dynamic, you see that the Ntk is the key to control how the loss decrease. So if this is a strictly positive definite matrix, then of course we can prove that the loss can always decrease. So this is the main idea to get the rigorous proof how to quantify how the loss decrease. Now that we have the decomposition, decomposing the Ntk into two parts, one part for A and one part for W. So because all these matrices are gray matrices, they're positive semi-definite. So we can discard the part for W and just simply focus on the part for A. If we can prove that during the whole training procedure, this Ka matrix is positive definite, strictly positive definite, then we can hope to get the convergence analysis, proving that Rs can decrease to 0. So this is the main idea of the proof. How we can control the smallest eigenvalue of Ka is the key of the proof. So so our goal again, let's recall our goal. Our goal is to prove that the neural network can approach to a function that can classify all the training sample exactly. In other words, we want to prove that the loss function will converge to 0. And by the dynamic in the previous slide, let us have a brief summary here. We want to quantify the smallest eigenvalue of this Ka matrix. If it is positive, if it is positive during the whole training, then we can expect that we can prove Rs going to 0. So how we can prove that the smallest eigenvalue is positive during the training? The idea is that we can do the analysis according to the following roadmap. So first of all, we introduce a stopping time T star. What is this stopping time? It is the first time the parameter trajectory go out of a neighborhood of the initialization. So at the initialization, we have the parameter set theta 0. We define a neighborhood of this theta 0 using the Fabrice norm of the Ntk matrix evaluated at the parameters. So T star is the first time this optimization trajectory go out of the neighborhood of theta 0. So we can prove some nice results when the training is within the neighborhood of the initialization. In other words, for T less than T star, we can prove the following nice results. First of all, we can prove that at the initialization, using some random matrix theory, the smallest eigenvalue of Ka, it's a positive number, very close to lambda s. This is the discrete Ntk, and lambda s is the smallest eigenvalue of the continuous Ntk. So this is first result. Second, we can prove that according to the gradient descent dynamic, when the neural width is sufficiently large, then we can maintain the smallest eigenvalue of the Ntk close enough to the smallest eigenvalue of the discrete Ntk at the initialization. Once we have these two observations, then according to the dynamic for the loss function, we can get a very nice control on the loss function. So according to this observation, we can expect that we can well control the smallest eigenvalue of the discrete Ntk during the whole training time until T star. So we can use the key property lambda s to control Rs, because the smallest eigenvalue is always approximately equal to lambda s according to these two observations. Because the smallest eigenvalue of Ka is always close to lambda s, by solving this inequality, we can get the next inequality controlling the decay of Rs. And from this result, you can see that when t goes to infinity, then the loss will decrease to 0. But you may ask the question here, can we let t go to infinity? The result of approximation and the inequality here is true only if t is less than t star, the stopping time. So to be able to make t equal to infinity, we have to prove that t star is actually equal to infinity. And this completes the proof of our optimization convergence analysis. In the interest of time, I will briefly give you some lemma to answer these red questions here, highlighted in red. So before the key lemmas, let us summarize the optimization convergence result. We can prove that under the random initialization in our setup, when the width is sufficiently large, much larger than polynomial in the number of samples and polynomial of 1 over lambda s, then we can prove that with certain probability over the random initialization, the empirical loss function can decay. In other words, in this format, in other words, we can identify the global minimizer of the empirical loss function. So what is in the result here? We need to understand how large this empirical loss function at initialization. If this one is very large, then the requirement is not easy to satisfy. And in fact, we can prove that the loss at the initialization is not very large. It has a scaling like this: gamma times square root of n, where gamma is 1 over n or 1 over square root of n. So the loss here is not very large. And next, I'm going to answer the questions in this slide, these 3 questions in red. So the first question is to show that we can prove that at the initialization, the smallest eigenvalue is close to lambda s. In fact, this is a very simple proof based on the law of large number, because the discrete Ntk is just the average of n samples of the random function defining the continuous Ntk. And we have assumed that the smallest eigenvalue of the continuous Ntk is equal to lambda s. So we can expect that when the number of sample n go to infinity, we can make sure that the smallest eigenvalue of the discrete Ntk will approach to lambda s, where n is the width of the neural network. So we can expect that if the width is sufficiently large, we can also prove that the smallest eigenvalue of the discrete Ntk is close to lambda s. Actually, we have the lower bound here. We are only interested in the lower bound. And the second one, we want to answer the question about during the evolution, whether we can prove that we can maintain the smallest eigenvalue close to lambda s. Actually, the proof is it's also possible when the width is sufficiently large. We can, if the proof is essentially some bound based on concentration inequality, we can prove that when the width is sufficiently large, all the parameters can stay around the initialization. Because the discrete Ntk is determined by the parameters, so of course, the smallest eigenvalue of discrete Ntk will stay around the initialization. Finally, we want to prove that T star is in fact equal to infinity. So how we can prove that? So the proof is it's not very difficult. So when T approach to T star, then by the definition, the trajectory of the parameter will go out of the neighborhood. By the definition of T star, it's the first time that this parameter go out of the neighborhood of the initialization. However, when T is less than T star, even though T is approaching to T star, according to the previous lemma, we know that the parameter will stay around the initialization with a distance bounded by 1 over n, where n is the width. So this means that when width is sufficiently large, then the parameter set will stay around the initialization. It won't go out. So this means that when n is sufficiently large, the stopping time T star is equal to infinity, and this completes the proof of the convergence analysis. So previously we have discussed the convergence analysis for regression problem. If we apply the convergence analysis for solving PDE, we can do the same thing. But the difference is that because we have the differential operator, so the differential operator changes the regression problem to a more difficult one. If we apply the differential operator to the neural network, we can get a very complicated neural network to fit a target function f. So the main difficulty is how to deal with the red term here with more difficult nonlinearity. But if we follow the same analysis, we can still prove that if we solve the second order PDE using the empirical loss minimization, we can also have the convergence analysis showing that we can identify the global minimizer of the empirical loss function when the width is sufficiently large. I will briefly talk about the generalization. Sorry for running over the time. So the generalization analysis is very standard in statistical learning. So we can just apply some standard technique in statistical learning to get the generalization analysis. For example, the radiometric complexity analysis. We can get a posterior generalization bound showing that for any set of parameter, we can quantify the bound of the empirical loss function and the population loss function with a scaling like 1 over square root of n. This is a very simple result based on the radiometric complexity. And based on this a posterior generalization bound, we have two ways to get the generalization bound for solving PDE. The first way is that we can put a hard constraint in the search space of parameter. For example, when we do the empirical loss function minimization, if we restrict the searching space to the parameter set that is bounded by a constant number in the L infinity norm, then according to the previous a posterior generalization bound and the approximation theory of neural network, we can obtain the generalization bound for this optimization problem. If we are able to identify the global minimizer of this optimization problem, then this global minimizer can generalize well with a generalization error like this. If the number of sample n is sufficiently large, the first term will be small. If the width is sufficiently large, the first term will be small. And then fixing the width, if the number sample is sufficiently large, then the second term is also small. The second way is to do regularization using a soft manner. For example, we can put a term in the loss function, and with this regularization, we can also prove that the global minimizer of this optimization problem has a good scaling in terms of the width n here and the number of sample n here. So I think that's all for my presentation. Thank you very much.
Thanks, Haizhao. Thanks so much for this very interesting and very impressive work. Any question so far?